Wonderful. Sorry, I'm in a bit of a, I've got to meet the high school class, but we'll talk to you later.
Okay, all right. Yeah. Okay, so good afternoon, everyone.
Couple of housekeeping things here before we start with or continue on with our lecture here. So we've got our term quiz 3 coming up Monday, Tuesday next week. So don't forget to find 60 minutes somewhere in those 2 days to complete that quiz. It's based on weeks 5 and 6, so it's based on the not this week's stuff that we've been talking about, but the previous 2 weeks. Yeah, I don't think I have anything else to say that I can think of. So any questions about things before we dive into the lecture here? Everybody's all good? Okay. All right. And I'm just going to further turn the brightness on this laptop down because this power cord that used to exist here, this power bar, has disappeared over the last few weeks. So I forgot to charge this laptop up fully before I came here, but hopefully it'll be fine. Anyway, so we are diving back in to action potentials here. So we just covered this slide a little bit on Tuesday, and we'll go into more details here about action potentials today. So just to kind of remind you of the 4 points there that I had mentioned at the end of lecture on Tuesday, we defined action potentials as being these brief, large reversals in membrane potential that can be propagated over long distances, such as the length of an axon, which we said can be quite long, up to meters perhaps, depending on the size of the animal, and they only occur in excitable cells. And so we had done a bit of a compare and contrast to graded potentials, because graded potentials, of course, can be longer lasting. They're not as large in magnitude. They are more local phenomenon because of the degradation. So we made that kind of compare and contrast between graded potentials and action potentials. Both action potentials and graded potentials, of course, can only occur in excitable cells, so they do share that trait in common. We mentioned how action potentials are also known as nerve impulses. You see that especially in some of the older literature, but even just when people are talking more casually, maybe let's say, they'll use that term. And we also noted that action potentials depend on voltage-gated channels, which we're going to go into much more detail about today, particularly voltage-gated sodium and voltage-gated potassium channels. And we had lastly noted that these voltage-gated channels are, for the most part, only found in those regions of the neuron that generate and conduct action potentials, which would be the axon initial segment and the axon. But we did put a little asterisk there and say that you sometimes do see voltage-gated channels present within the dendritic zone, and there they act as kind of signal boosters. And what I meant by that was, if you imagine for a moment that you've got some kind of gated sodium channel that's in your dendritic zone, allowing you to respond to, I don't know, say, touch, for example, we know that those graded potentials are going to decay as they travel from where that touch sensation was detected. They're going to decay as they are traveling through the dendritic zone to the axon initial segment, and they may decay to the point of becoming subthreshold at some point, and then they can't actually cause an action potential to occur. If you want to kind of give a boost to that signal that's decaying, you can basically have voltage-gated sodium channels along the way, so that ultimately, as the graded potential is passing by a certain region of the membrane on its way to the axon initial segment, it can trip these channels to open and allow for an additional influx of sodium ions to occur, right? And then you have basically boosted your graded potential at that point, and then that boosted graded potential can travel on, and it just increases the chances that you're going to actually have that stimulus that initiated that graded potential cause an action potential to occur within this neuron. All right, so that's one other way that we can use these voltage-gated channels. So let's go through and let's look at the figure that I have here, and let's try to understand the shape of the action potential. How does the membrane potential change here, and how is this connected to these underlying voltage-gated sodium and potassium channels? So we'll start here at resting membrane potential, good place always to start. And so we're at that typical kind of negative 70 millivolt value that we think of as the resting potential for neurons. And we can see here in this figure that it tells us that in the resting state here, our voltage-gated sodium and voltage-gated potassium channels are in their closed state, right? So they're not allowing any sodiums or potassiums to currently pass through them. We do have to remember that we have still potassium and sodium leak channels, right? So they would be open because they are always open. That's their defining feature. And so that's what's establishing our resting membrane potential. But when we're at resting membrane potential, these voltage-gated sodium and potassium channels are closed. Now, what's going to happen next here is we're going to subject this neuron to a stimulus. It's specifically going to be an excitatory stimulus or a depolarizing stimulus. And so in response, we're going to get a graded potential, right? So here's our graded potential, our shift from the resting value to a more positive value in response to whatever stimulus has been applied here. And what we'll notice is, again, the whole time that the membrane potential is increasing towards the threshold value, again, these two channels, the voltage-gated sodium and voltage-gated potassium channels are still closed, even as the membrane potential is now rising and becoming more positive. These channels are still closed. However, at the point where the graded potential gets us to the threshold potential value, that is when these voltage-gated channels are going to be signaled to open. So we know that the stimulus for a voltage-gated channel is a change in membrane potential. And so in particular, the stimulus for these voltage-gated sodium and potassium channels is getting the membrane potential to the threshold potential value. That's the particular stimulus that they are looking for. They're looking for the membrane potential to get to or even above the threshold potential value. That is the stimulus that is going to activate the voltage-gated sodium and voltage-gated potassium channels. Now, what we have to appreciate, and what they highlight for us here, is that when we get to the threshold potential, that is the stimulus that causes both the voltage-gated sodium and potassium channels to open, right, to become active, to open, to allow ions to pass through. But you'll notice that they don't open at the same speed, right? They, in particular, highlight here that the voltage-gated potassium channels only activate slowly, whereas the voltage-gated sodium channels, although they don't really specify it here in the figure, the voltage-gated sodium channels, they activate and open very rapidly. So what's important for us to recognize is both of these voltage-gated channels are activating and opening in response to the same stimulus, right, in response to getting to the threshold potential value, but they differ in terms of the speed at which they open and activate in response to that stimulus, right? And so because the voltage-gated sodium channels open and activate very rapidly, right, that's why the first part of the action potential here is a depolarization phase. Because you now have your voltage-gated sodium channels, they are open, right? They are activated because we got the threshold, and they responded to that threshold stimulus very rapidly. And so now sodium is able to start coming through the membrane more easily. You've increased the sodium membrane permeability. And so we know, as we talked about last week, when you increase an ion's membrane permeability, what's going to happen is the membrane potential starts moving towards that ion's equilibrium potential. So because we know that sodium has a very positive equilibrium potential, we can see that when we activate these voltage-gated sodium channels very quickly in response to that threshold stimulus, we see now that we've increased the sodium membrane permeability, and we see this quite rapid depolarization, this quite rapid change in membrane potential as it's moving towards the very positive equilibrium potential value for sodium. Again, I want to emphasize, I'm going to use a little analogy here for this, that, again, both the voltage-gated sodium and potassium channels are opening and activating in response to the same stimulus, in response to getting to the threshold potential. They just open and activate at different rates in response. And the analogy I always try to use here is to imagine for a moment, if you can, that my wife and I are lying together in bed, right? And if it makes you feel better, picture us with clothes on, but we're lying together in bed. That joke works better when there's more people to laugh at it. I feel like we need more people just so I hear more laughter. Everyone here now has to laugh harder at any jokes to compensate for the smaller number of people. Anyways, the alarm clock goes off in our house very early in the morning, mostly because the kids are in high school, and high schools start ridiculously early. And so the alarm clock goes off in the house at 6 a.m. And so when I hear the alarm clock go off, right, that's my stimulus to get up and get going. And I'm like out of bed, into the bathroom, brush my teeth, get dressed, ready to go for the day. When my wife hears that same stimulus, right, she hears it, but then she kind of turns and tosses, and maybe 10 or 15 minutes later, she's finally up and out of bed. So we're both, starting our day in response to the same stimulus, the alarm clock going off, but we've responded to it in different rates, right? So I am the voltage-gated sodium channel in our marriage, and she is the voltage-gated potassium channel, right? We've not yet gotten t-shirts that say that, but that day is coming, I think. So anyways, again, threshold potential is our stimulus. The voltage-gated sodium channels open up and activate in response to that stimulus very rapidly. Hence, we have this depolarization phase. And then it's only a little bit later that the voltage-gated potassium channels are finally activated. And just as they're getting fully activated finally, the voltage-gated sodium channels spontaneously undergo an inactivation, which we'll examine in more detail in a second. But this then leads to the second phase of the action potential, which is a repolarization phase. Because now you have returned the membrane sodium permeability back to its resting values, because you've got these inactivated, impermeable voltage-gated sodium channels. And now finally, you've got your voltage-gated potassium channels fully open. And so now the membrane potential is going to start moving again towards the equilibrium potential for potassium, which we know is a very negative value. And so that's why we start to see the depolarization phase ends and the membrane potential begins to move in the more negative direction because of all that potassium permeability. It's trying to get to the equilibrium potential for potassium. Now, eventually, the repolarization is going to bring us back to and then just below the threshold potential. And once we come back below the threshold potential, that is the stimulus that tells both the voltage-gated sodium and potassium channels that it's time for them to close again. All right? Now, they close again at different speeds. The voltage-gated sodium channels close very rapidly. Now, in this case, they're going from an inactive state to a closed state, so that change is kind of a moot point when it comes to membrane potential, because you're going from one state that wasn't letting sodiums go through the membrane to another state that isn't letting sodiums go through the membrane. No big deal, no big change. But the potassium channels here, they only close very slowly. Just like they open slowly, they close slowly. And so the consequence of that slow closing is that even once we get down below the threshold, and there's been this signal for the voltage-gated potassium channels to close, because they close slowly, we still have lots of potassiums flowing across the membrane. And ultimately what happens is we actually find that the membrane potential briefly goes more negative than the resting potential, right? It gets very close to potassium's equilibrium potential. And this we refer to as an after hyperpolarization, where the membrane potential has actually gone down below, more negative than the resting membrane potential, getting very close to the equilibrium potential for potassium because these potassium channels are closing very slowly, right? So there's still enough of them open for long enough to allow for the membrane potential to get below the resting value, get pretty close to potassium's equilibrium potential. Once those voltage-gated potassium channels finally close, then you're going to be back to the resting membrane potential, because now the only channels that remain open are the leak channels, and so we're going to go back to the resting condition. All right? So this is how we get this particular shape, if you will, to an action potential, right? It has everything to do with the opening and the closing and the inactivation of these various voltage-gated channels, and the speed, the relative speed at which they both open and close. Okay. The other thing that I wanted to just briefly highlight here, we'll come back to it, but since I mentioned it here, it seems like a good time to talk about it, is at the very top of this figure, they introduce us to this idea of the refractory period. And so refractory in this case means basically unable to or less able to generate another action potential. So that's what we're talking about here in terms of refractory. And we have these two different refractory periods. So one is called the absolute refractory period. So during this period of time, you absolutely cannot get another action potential to be generated. And then you have, after that, the relative refractory period, where it's possible to generate another action potential, but it's relatively harder to do so, meaning that you would need a stronger stimulus to cause that second action potential to occur compared to the strength of the stimulus that was required for the original action potential. So what's causing these refractory periods? Well, let's start with the absolute refractory period. And let's start by kind of thinking back to what we were just talking about. What needs to happen to start an action potential? Well, what starts an action potential is the opening of the voltage-gated sodium channels. Right? That's the very first event, and that leads to the depolarization phase. Well, throughout the entire absolute refractory period here, okay, we are not able to open these voltage-gated sodium channels, which means we can't generate another action potential. The reason we can't do it is twofold. During the depolarization phase, those voltage-gated sodium channels are already open. You can't open something that's already open, right? If you have an open door and someone says, open the door for me, you'd probably just look at them kind of funny, like the door's already open, like what am I supposed to do here? You can't open an already open channel. So when we're in this depolarization phase of the action potential and the voltage-gated sodium channels are already open, they can't be opened again. So we can't generate another action potential within that depolarization phase. And then, during the repolarization phase, the voltage-gated sodium channels are inactivated, and you cannot open voltage-gated sodium channels from the inactive phase. They can only open from the closed phase. And in a moment, when we go into a bit more detail here, we'll see why that is. So the idea here is that the entire time that the membrane potential is above threshold, whether depolarizing or repolarizing, we're in the absolute refractory period, where we are unable to generate another action potential because we are unable, for one reason or another, to open the voltage-gated sodium channels. Once we come below the threshold potential, we switch over into the relative refractory period. Now, because the voltage-gated sodium channels are closed and we can open them from that state, in the relative refractory period, we can now generate a second action potential because we can open these closed voltage-gated sodium channels. But in the relative refractory period, it becomes relatively harder to generate that second action potential, largely because of how the voltage-gated potassium channels are still open. And so they're causing a hyperpolarization to occur, right? They're letting potassiums flow across the membrane, and it's causing this membrane hyperpolarization, and that hyperpolarization is pushing us further and further away from the threshold, which means to get us back to threshold so we can generate another action potential, we're going to need a relatively stronger stimulus to oppose that potassium hyperpolarizing effect, to get us back to the threshold to generate another action potential. So that's why it becomes relatively harder and why a stronger stimulus is needed within the relative refractory period to get that second action potential. Once those voltage-gated potassium channels close and you're back to the resting condition, then you leave the refractory period. And you're back to the point where I can generate a second action potential, and all I need is the same stimulus that I had in the first place that caused the original action potential to occur. Okay? We'll talk about that again a little bit later, but I wanted to introduce it since it's right there, and I think it fits nicely with our conversation about action potentials. Now, another point I want to drive home, and I've driven this point home before, so it's more of a review. Again, we acknowledged earlier in the course that it only requires only a small number of ions actually have to move across the plasma membrane to cause a significant change in membrane potential, right? And so even though we're going from negative 70 here to positive 30 at the peak of this action potential, which seems like an impressive change, it's a 100 millivolt change, again, we have to recognize that because the plasma membrane is so thin, the absolute number of sodiums that crossed the membrane here to cause this change in potential from negative 70 to positive 30 is actually very small. The absolute number of ions moving was pretty small. However, as it kind of notes here, if you are doing action potential after action potential after action potential, your brain or your nervous system is really highly active, right? Then although each individual action potential only involves a fairly small number of ions moving across the membrane, if you were to add that up over the course of all the action potentials that are happening in your nervous system, I mean, eventually you get to the point where, now a significant number of ions have actually moved across the membrane, and we need to get those ions back to where they started to help us maintain ion concentrations in our extracellular and intracellular fluids, to help us maintain, certain specific equilibrium potentials and membrane potentials and whatever. So we've already acknowledged earlier that that's the job of the sodium-potassium ATPase, to pump these sodium and potassiums back across the membrane, right? So that's happening at resting potential, right, where we have, a small number of ions leaking across the membrane to establish the resting potential, and the sodium-potassium ATPase pumps them back. But then when we are doing, when we are responding to stimuli, and we're generating all these action potentials, and now we have additional ions that are moving across the membrane with each action potential, we again need that sodium-potassium ATPase to become a bit more active and start pumping these additional ions back to where they came from to help us to maintain those proper sodium and potassium ion concentrations that, again, influence what the value of our membrane potentials are going to be. And so, we've already acknowledged that, that this happens, but, and I'll come back to that point in a second, but let me just maybe jump here first, which is to basically say that, we've already recognized that, neurons, they have very high metabolic rates. Neurons are very energy-intensive cells, right? And a big part of the reason for that is because they are using this sodium-potassium ATPase and running it at very high levels in order to pump all these ions that are moving across the membranes with every action potential that occurs, right? And so, your neurons need a lot of glucose. They need a lot of oxygen. Your neurons are not very tolerant of hypoxia. They're not very tolerant of hypoglycemia. This is why, people pass out if they are deprived of oxygen or become hypoglycemic, because the neurons are continuously using tons of energy to pump ions back across membranes in opposition to their flow during every action potential, even in opposition to their flow at resting potential, and they need a lot of glucose and oxygen to power all that ion pumping. The figure that I have here kind of shows us what happens to our action potentials if we shut down this sodium-potassium ATPase for a period of time. We already acknowledged earlier in the course that there is this inhibitor called wabane that can inhibit the sodium-potassium ATPase. And so this figure here, now these are cardiac action potentials. That's why they look a little bit different. I couldn't find any good illustrations that were about neuronal action potentials, but the basic idea is the same. The line that's marked with the C, so that's the control. So you can kind of see that it goes up to a nice peak here, and then in the cardiac case, it kind of slowly returns down for a bit, and then rapidly comes back to rest. So you can still see depolarization and repolarization phases. It's just that you have this kind of prolonged time in between them. That's typical of cardiac action potentials. Anybody that's taken C34 with Stephen Reed will know that like the back of their hand, I bet. But then if you look at the line mark number 20 here, this is what's happening to action potentials now 20 minutes after we've exposed these neurons to wabane. So we've shut down their sodium-potassium ATPase for 20 minutes, and you'll notice that the action potential looks very different. Number one, you'll notice that it doesn't quite get to the same high positive peak as the control does. And that's because if you have shut down the sodium-potassium ATPase, you're not able to pump sodiums back across the membrane as they come in with every action potential, so the sodium concentration gradient starts to get a little bit smaller. And then correspondingly, its equilibrium potential gets a little less positive. And so when you are triggering an action potential, sodium isn't shooting to get to this really high positive equilibrium potential anymore. It's only kind of shooting towards this sort of smaller, less positive equilibrium potential. So you don't get as big a peak here. And then you'll notice that in the control, we eventually had that kind of rapid repolarization at the end. That's not happening here at all in the Wabane case. It's just a slow, steady repolarization back to rest. Again, that's because you're losing your potassium gradient. And so potassium is losing its drive to like rush across the cell to get back to its own equilibrium potential. There isn't that big potassium gradient now if you're shutting down the sodium-potassium ATPase, and so there isn't as big of a disequilibrium for potassium between that smaller positive peak and its own equilibrium potential. It's not being driven to go across that membrane as rapidly, and so you get a lot slower repolarization phase. So again, it's important for us to recognize the sodium potassium ATPase definitely has a role to play in terms of pumping ions back across the membrane, after every action potential, to help us to maintain constant ion concentrations in our extracellular and intracellular fluids, which allow us then to have consistency, in all of the action potentials that we are forming within our neurons. Okay, so I want to dig a little bit deeper here now into the voltage-gated potassium, dig a little bit deeper into the voltage-gated sodium channels here, just so we can appreciate how these things work, because obviously they're very critical to action potential formation and therefore nervous system function overall. So you can see here again, there are 3 different states that the voltage-gated sodium channels can be in. So they're either in a closed state or an open state or in an inactivated state. All right? They are a type of gated channel, so that means they have gates, right? Gates that can be open or closed. So let me introduce you to the gates here. There are 2 gates on voltage-gated sodium channels. They have what's called an activation gate, so that's this green gate here. But they also have an inactivation gate. This sort of, what's pictured here is kind of this white ball on the end of a little black chain there. So these are double gated channels, right? They have an activation and an inactivation gate. And the key is that if either of those gates are closed, then sodium ions are not able to flow across the membrane through these voltage-gated channels. Okay, so let's start here in the closed state. What you'll notice is in the closed state, the activation gate is closed, but the inactivation gate is actually open. Now again, it only takes one gate being closed to block ion flow here, so you can see there are no sodium ions being shown as flowing through here in the closed state because the activation gates are closed. All right? And so this will be the state of voltage-gated sodium channels whenever we are below the threshold potential. As long as we're below the threshold potential, these voltage-gated sodium channels will be in this closed state. Now, what keeps them closed in response to being below the threshold potential? Well, notice here that within the structure of these channels, you have these voltage-sensing alpha helices, right? These kind of red or purple or whatever pink structures here. These voltage-sensing alpha helices, and you'll notice that they are very highly positively charged. There's lots of positively charged amino acid residues that make up the voltage-sensing alpha helices. And so because they're positively charged, and because at resting potential, the inside of the cell membrane is negatively charged, those voltage-sensing alpha helices are kind of drawn inward, right? They're drawn towards the cytosolic face of the plasma membrane whenever we're at resting membrane potential, whenever we're below the threshold potential, right? And as long as those helices are kind of pulled inward like this, they will cause the activation gate to be closed. They control the activation gate. So we're below the threshold potential, right? We're at resting potential, let's say. It's kind of negative on the inside. These positively charged helices are attracted to those negative charges, so they're shifted in the inward or cytosolic direction, and that's causing the activation gates to be closed, so no ions can pass through this channel at this time. If we have a graded potential that brings us up to the threshold potential, well, now when we get to the threshold potential, it's not going to be positive on the inside as they show here, but it's more positive than it was at rest. And because it's suddenly more positive than it was at rest, when we get to that threshold potential, that more positive kind of ends up, again, it's still negative, but not as negative as it was. So there's not as much of an inward pull on those positively charged helices because your membrane potential has become less negative, more positive. It's not going to be pulling those sensors inward as strongly. And so without that pull inward on those helices, they pop outward. They pop out towards the extracellular side of the membrane. And as soon as they pop outward, then that causes the activation gates to open. So now you've got your activation gates open, and you've got your inactivation gates still open, so the channel overall is in an open configuration. And you can show, or see now, they're showing how sodium ions are now flowing through this now open voltage-gated sodium channel. So again, getting to the threshold potential meant that you didn't have that strong inward negative charge to pull those positive sensors inward anymore, so they pop outward, the activation gates open up, both gates are now open, and sodium ions can pass through. This will give us the depolarized phase of the action potential. What happens next is that the channel goes from being open to being inactivated. All right, and how that happens is the inactivation gate is going to just spontaneously swing into place. It's going to spontaneously close. And as soon as that inactivation gate closes, now again, you can't have ion flow through the channel. So you can see they're no longer showing any ion flow through the channel. The activation gates are still open, mind you. It's the inactivation gates that are now closed, and this leads us to the inactivated state of this channel. So you can see here, hopefully, how closed and inactivated are different. Closed means that you have your activation gate closed. Inactivated means you have your inactivation gate closed. They're different configurations because they're different gates that are closed. The end result is the same. There's no sodium ions passing through the channel, but it's for a different reason. Different gates are closed in these different states. All right? We're going to talk about the kind of spontaneous closing of the inactivation gate in just a second, but what I want to highlight next here is that the only way to get the inactivation gate back open is to close the activation gate. The closing of the activation gate forces the opening of the inactivation gate. That's the only way. Now, how do we close the activation gates? Well, we have to get our membrane potential back down below threshold. Because once we get our membrane potential back down below threshold, it'll be negatively charged enough in the inside face of that membrane to pull those voltage-sensing alpha helices back inward, and then that will cause the activation gate to close, and then that will force back open the inactivation gate. And so the only way for us to kind of open that inactivation gate and get out of this inactivation state is to go back to the closed state, which again required us to go back down below the threshold in order to allow those sensors to come back inward, to force the closing of the activation gates, and force the opening of the inactivation gates. So this is why we can't go from the inactivated state back to the open state. There's no way to go there because the only way to open the inactivation gate is to force it open by the closure of the activation gate, right? And so we are forced to cycle through in a particular order here, right? We have to go from closed to open to inactive back to closed, right? That's the cycle here. There is no possible way to go from inactivated to open, right? At least not without there being some problem here, right? If there's some problem with your inactivation gate, it's got a faulty latch or something and it closes and then just like, rusty hinge and it opens up again, like, okay, that can happen, that's a pathology. But physiologically, it's always going to be closed to open to inactive back to close, okay? So then again, this helps us to kind of go back to when I was talking about the absolute refractory period. Why can't we have a second action potential occur during the repolarization phase of the action potential? It's because the voltage-gated sodium channels are inactive at that point, and the only way to get them out of that state is to come back down below the threshold potential, right, to force the activation gate to close and push the inactivation gate open, right? There's no way to go from inactive back to open. So as long as you're in that repolarization phase, as long as you're above the threshold potential, there's no way to reopen those voltage-gated sodium channels. Now, I do want to highlight here exactly how this inactivation gate closes, because so far I've just described it as being kind of a spontaneous process, right? Because one of the things that they actually highlight here in this figure that I should point out, I mean, the channel is only open for a very short period of time, right? I mean, the channel opens for maybe a half a millisecond to a millisecond, and then spontaneously the inactivation gate closes. So what's causing the inactivation gate to close? Over the years, there have been many different models that have been kind of proposed for how this works. This model I'm going to propose here seems to be the current favorite, okay? But I'm not saying that if you took the course, 2 or 3 years from now, neuroscience might have changed a bit. We might have a revised model, but this seems to be the current favorite model. So the picture up here in the top is again showing us our voltage-gated, well, the whole thing here is the voltage-gated sodium channel. And so right now you can see that it's in its closed state, because there's the activation gate blocking the channel, right? And so we're clearly in the closed state here, and we don't see any closed inactivation gate. So yeah, we're in the closed state here with the activation gate being closed. What I want to draw your attention to is this region of the voltage-gated sodium channel called the IFM motif. So this is 3 amino acids, so isoleucine, phenylalanine, and methionine, right? IFM, those are the 3 one-letter codes for those amino acids. This motif has been well identified as being a critical player in the closing of the inactivation gate. What you'll notice here is that when the gate's in its closed configuration, there's no place for this IFM motif to bind. So it's just kind of sitting there doing nothing, okay? And hence, the inactivation gate is currently open. But what happens is when the activation gates open, okay, and so that's triggered by, again, that outward movement of those voltage sensors, you'll notice our activation gate has opened up here, right? So it's out of the way, it's opened up, and sodiums are passing through. Notice what else happens here. If you look at these orange regions, what they call the S6 helices, which basically are the protein, the part of the channel that lines the actual channel. It's the part of it's the part of the channel that is the lining of the channel. This is where the sodiums are going through, right? Is in the space between those S6 helices. What you'll notice is that when we go into the open configuration, right, because of the movement of those voltage sensors, and that triggers the activation gate to open, notice how, if you pay close attention to this little region here, notice how it undergoes a conformational change. So when the gate goes into its open state, that S6 helix there undergoes a conformational change to expose a binding site for that IFM motif. And so when the IFM motif senses that there is this binding site now on this S6 helix, it binds to it, and then that is the trigger for the closing of the inactivation gate. So let's just go through this one more time just to make sure we feel good about this. We're in our closed state, right? Activation gate is closed. Voltage sensors are directed inward. IFM motif is currently not bound, so the inactivation gate is open. We get up to the threshold potential. the voltage sensors pop outward, causing the activation gate to open. So now we're in our open configuration. There's also a change in the conformation of the S6 helix to create this little binding pocket for the IFM motif. It then binds to it, and that is the trigger to cause the inactivation gate to close, and now we're into the inactivation state. Again, the only way to get that IFM motif to unbind so that the inactivation gate can open up again is for those voltage sensors to come back inward, right? To cause that S6 helix to go back to its original conformation where IFM couldn't bind, and then IFM will unbind, the inactivation gate will open, the activation gate will close, and we're back to the closed state. All right, so that's the current model for how this inactivation gate closure works. Okay, it used to be thought, if you happen to be reading older papers, it used to be thought that the IFM motif was the gate itself. And that model is kind of falling out of favor, and this model has kind of come in with more details to replace that outdated model. Voltage gate potassium channels, as my point says here, we already know that they are slower, right? They're slower to open, they're slower to close. We've already emphasized that. They're similar in terms of their structure here. The biggest difference is they don't have an inactivation gate. They're just single-gated channels. They've got an activation gate that can either be open or closed, so there's only two configurations. For a voltage-gated potassium channel, it's either open or it's closed. Sodium voltage-gated channels have three configurations: closed, open, inactivated. Voltage-gated potassium channels only have the two states, closed and open, because they lack an inactivation gate. All right, the next thing I want to talk about here is local anesthetics. So we know now that voltage-gated sodium channels, we know a lot about them now. We know that they are critical to initiating action potentials, and we know that action potentials are critical to nervous system communication. So if we can shut down these voltage-gated sodium channels and thereby stop action potentials from occurring, we can basically shut down nervous communication. And that can be useful in some contexts, like, for example, when we don't want to feel pain, right? So local anesthetics, these are drugs that are administered to a certain specific region of your body to basically shut down nervous communication in that localized region where they are injected, okay? So contrast that with general anesthetics, right? If you've ever gone to maybe a surgical procedure where they've knocked you out completely, that was a general anesthetic, right? They hooked you up to the gas, or in rarer circumstances, they may have injected you with something, but they hook you up to a gas that you breathe in, right? You just go unconscious, and you wake up sometime later, and you're like, what the hell did you do to me, right? And hopefully you consented to whatever was happening there, but whatever. I don't want to derail myself here. But a general anesthetic just, renders you unconscious, knocks you out, you perceive nothing anywhere. A local anesthetic is injected into a specific region of the body to just inhibit nervous communication there. And so most commonly, local anesthetics are used to inhibit you or prevent you from feeling pain in a certain region. So dentistry is a major place where local anesthetics get used, so hence the picture here. So here's a woman who's having lidocaine, which is an example of a local anesthetic. She's having lidocaine injected into her mouth. Presumably the dentist is going to be kind of working in there, doing something that would cause pain, and so we use the local anesthetic to basically numb the pain, right? Oftentimes you hear this as a freezing agent, right? That's what people will say. I'm going to freeze your mouth right now, right? It's not what they're doing. It's not like they're injecting something that's going to drop the temperature down. They're literally just trying to block the pain signal communication from getting to your brain. Okay, so that's how local anesthetics work. We actually know pretty precisely how these local anesthetics do what they do. They are inhibitors of voltage-gated sodium channels. As kind of a side note, general anesthetics, we're still kind of learning how they work. We know they work. We give them to you, you go unconscious, you wake up later, it happens. But there's still a lot of question marks in terms of what the hell are these things actually doing? And we know they do what they do and they work, but we don't know them mechanistically very well. By contrast, local anesthetics, we really know them well at the mechanistic level, okay? So where I'll start here is by looking at the chemical structure of local anesthetics. All local anesthetics have the same chemical structure in that they have three major parts to them. They all have an aromatic ring. Okay, you see that here in the structure of lidocaine, an aromatic ring. They all have a terminal amine group. So here you see that here. There's my terminal amine here. And they all have either an ester or an amide linkage that joins the aromatic ring to the terminal amine. And here you can see in lidocaine, we have our amide linkage. So that is the structure of every single local anesthetic. Now, there are many different kinds of local anesthetics, and what makes them different from each other is these R groups, right? These things that are substituted on to the aromatic ring or the terminal amine. So if you look, for example, at lidocaine, you can see there's a couple of methyl groups here that are attached to the aromatic ring. And similarly, we've got here a couple of, I think these are probably ethyl groups here that are attached to the terminal amine. Right? So the substituents that are added on to the aromatic ring and to the terminal amine, those differ between different local anesthetics. And that's what makes the specific properties of every local anesthetic a little bit different. All right? So let's kind of talk about how the chemistry links to the actual function, the properties of these local anesthetics. So let's start here, I guess, by just thinking about how do these local anesthetics actually inhibit the voltage-gated sodium channels. We have to appreciate that first, and then we can look at their chemistry and the mechanism. The first thing I'll point out is that local anesthetics are injected into the body in a protonated form. Okay, so they have a positively charged kind of proton here on them. If you look, for example, at the bottle of lidocaine here, it says lidocaine HCl, right? So the H is going to be our proton that's bound to the lidocaine. The chloride there, the Cl, is just the counter anion for electroneutrality. Okay? So we always inject local anesthetics in these protonated forms because that makes them water soluble. Okay? In that protonated form, these local anesthetics are water soluble. Right? So we can make them up in, say, saline solutions and inject them into the body in that form. However, in order for local anesthetics to actually do their job, to inhibit the voltage-gated sodium channels, they actually have to get inside our cells because they inhibit from the inside face. You can see them here. They bind to the inner face, the cytosolic face of the voltage-gated sodium channels. That's their inhibitory site. So we inject them into our bodies, into our extracellular fluids, and then they have to get across the cell membrane to get inside the cell in order to do their job. Well, in order to get into the cell, they can't be protonated. They have to get rid of that proton. So deprotonation has to occur to give you now what is basically just a nice kind of hydrophobic group that can then easily cross the cell membrane. And then once inside the membrane, it has to reprotonate because it actually inhibits in the protonated form. Okay, so that's what we have to appreciate, right? That this deprotonation is necessary for the local anesthetic to become membrane permeable. It then crosses into our neurons, reprotonates inside, binds to the interior face of the voltage-gated channels, blocks them from transmitting sodium, therefore stops action potentials from occurring. All right? So, there are two fundamental properties of local anesthetics, and I'll just briefly mention them here, and I'll have to pick it up again tomorrow. But one of the properties is how long does it take for this local anesthetic to start working? The so-called time to onset, right? It's how long between the injection and when you stop feeling pain, right? How long does that take? The major determinant of that is how quickly can this local anesthetic deprotonate so it can start getting into your cells. And so the major part of the chemistry here that determines time to onset is the terminal amine, because that's the place where the proton is bound and has to unbind. Okay? So how quickly can that terminal amine dump its proton to then give you this now hydrophobic drug that can cross the membrane and start inhibiting? The faster the anesthetic can dump its proton, the faster that terminal amine can dump its proton, the faster this drug can start working. Okay? And I'll talk a little bit more about that tomorrow. The other part that's interesting here is the potency, right? How potent is this drug? Which is to say, like, to what degree can it knock down your pain sensation? That entirely depends on the aromatic ring. Because what determines the potency is how much of this drug can actually get into your cells. And that's largely determined by how hydrophobic is the deprotonated form of this drug. The more hydrophobic the deprotonated form of the drug is, the more easily it can cross into your cells to get to those voltage-gated sodium channels to inhibit them. Okay? So I'll stop there, and we'll talk a little bit more about this tomorrow. I guess I want to talk about, again, how different local anesthetics have different potencies and times to onset, and how that's determined. So we'll pick that conversation back up there. Enjoy the rest of your afternoon, and I'll see you tomorrow. Oh, okay. Okay. Yeah, we can find it. Yeah, maybe send me an email, and then I'll try to find. Usually, like I don't know. Do you come to lecture on the Friday?